Hello everybody. Based on public demand, I'm now recording the Salishan talk that I gave at the Salishan meeting earlier this year on Exascale cloud computing, a foggy tale of networks, AI, and containers. And actually, in Switzerland, we also have Exascale. And this is something, if you look at this wonderful mountain that we have here, the Matterhorn. So how heavy is the Matterhorn? So you can ask your favorite AI model to help you. Here I asked the Bing Chat, or what's now called Copilot, to explain me how heavy the Matterhorn is. And it turns out that it's 17 exagrams, so which is nearly as good as, as 15 exaflop AI, isn't it? At least generated by an AI model. But yeah, jokes aside. So cloud computing. So how do we deal with cloud computing today? Well, one of the issues with cloud computing is that it recently changed to be a pure service to web services and data services to actually a service that offers high performance services, such as AI training, AI inference, or even HPC simulation and weather prediction services. So here, this is why we came up with the idea as acceleration as a service. We know all of these various as a service things like infrastructure as a service, software as a service, platform as a service. But what's missing today is a clear definition for how do we provide compute acceleration as a service. So fortunately, there was a special issue of Computing in Science and Engineering ran by many people and many friends, including Bill Magro, where we contributed a paper that we call XaaS, Acceleration as a Service to Enable Productive High-Performance Cloud Computing, outlining the idea how to actually do acceleration as a service. And we even have a wonderful rabbit, fast-running logo, AI-based logo here. So, but what does it mean more technically? Well, first of all, everything is software. In high-performance computing, we're currently living in a compile and run development, run-to-completion jobs with performance libraries and abstractions, much of that developed by Jack Dongarra. Traditionally less security conscious because we really don't care about security in a closed setting, and the computer hours are allocated fixed. And it really operates under the assumption high performance first. So we want to make optimization a primary target of our codes, which you can already see in the list of things. Cloud computing is very different. Cloud computing is always about productivity, simple deployments. Microservices, functions are kind of like library calls, but in a cloud computing setting. So you communicate through really slow interfaces like REST and JSON, and you have security as a first-class citizen because literally anybody with a credit card gets access to that system. So it has to be very secure in some sense. But then, as I mentioned, credit card, you pay with real money for usage, which is also a different usage model as many of the high-performance computing systems. So somehow this benefits the ecosystem and the market. So we want to foster accessibility. And these two, high-performance computing and cloud computing, have so far been quite different from each other. But I believe, and many people with us believe of many people who share co-authorship of this paper, have the same belief that we should converge these two as an acceleration as a service offering in the cloud or in on-prem system. So this would get us basically high-performance portable containers. We need high-performance communication and I/O, and we need high-performance allocation and accounting, all very productive as the cloud. So really, what a good goal for this acceleration as a service would be on-demand high-performance cloud computing for long-running HPC-style jobs. Actually, today, the longest running jobs are machine learning training jobs that are running on HPC systems. So keep that in mind. And now at the end, what we want to do is we want to merge the two, cloud computing with its virtual machines and supercomputing with its compiled source coded applications, into portable XaaS containers that give us all of these benefits outlined here on the right side. Right? So this is the high level picture. Really, productivity and efficiency are probably the most ones, actually portable efficiency even. The most important one. So how do we do this? Well, we propose a layered stack. In fact, at the bottom, we have compute providers, either cloud providers or HPC service providers. These compute providers are very, very specific. So they're market specific, they have specific policies, they could be public, they could be private, but this is what we essentially have today. Then we need a portable interface to move between these compute providers. A standard API, for example, the OCI, the Open Compute Infrastructure APIs are a very good start in that idea. Then these cloud providers typically have base operating systems where they offer you containers which are Ubuntu, Debian, POSIX compatible containers. But these are somewhat generic and often also run through a system called Docker or many other of these orchestration systems. And then what we propose is to have a XaaS layer where we now have the compute acceleration, communication, and I/O libraries and APIs on top of the base operating system layer. So this is really system specific. So there would be libraries for HPE machines, libraries for Intel machines, library for NVIDIA machines, and libraries for Microsoft Cloud, for example, or for GCP Cloud or AWS Cloud. Even if you don't reveal the underlying architecture, like many of these cloud providers do, you could offer optimizing libraries in the portability layer to your customers. Very much like MPI used to be in the good old days. And this must all be maintained by the provider, because the provider is the only one who knows all the details about the infrastructure in case the provider wants to keep it confidential. And then the community could build simulation platforms on top of this for climate computing, QCD, materials, all of those. Or they could even offer service platforms serving climate data and materials data to the wide public. And this is then domain specific, for example, the climate domain, and maintained by a community. So these are the layers for acceleration, for an architecture as acceleration as a service. So now, the question is now, well, can we converge cloud and HPC infrastructure? And now, looking at the state of the art in 2022, what are actually the differences? Because before you converge anything, you would need to understand what the differences actually are. The top 4 are clouds, the bottom 3 are on-premise systems like Dyn, the Alp system, or the Deepest system. If you look at the CPUs, they're all very similar. It's all x86, faster or less CPUs, so no big difference. The network bandwidth is also comparable within a factor of 2. That's great. However, the network technology and the transport protocols are wildly different. And this leads me to the idea that we need to converge hyperscale data center and high-performance computing networks, because as we can see on the previous slide here, this is the only thing that largely differs. So we really should think about having the same infrastructure. Now we need to consider multiple factors. We need to consider differences in design and deployment, operation philosophies, service diversity, protocol stacks, and utilization. So these are all things I don't want to go into too much detail here, but if you wanted to understand this in more detail, you would read this paper and you would understand what the differences today are in cloud provided networks and on-prem high-performance networks. But in fact, they're not too large. So now the question is, what are the workloads? What are running on these networks? So now we figured out that the differences in the technologies are not too large, so enabling convergence. But now we should think about, could we also enable convergence for the workloads? Are they very different? Well, first of all, I want to classify the workloads by their bandwidth sensitivity and later latency sensitivity. So we have, from a network perspective, there's really mainly bandwidth and latency. So here we have bandwidth, which is essentially a matter of cost. So you can just buy more expensive NICs or more of those expensive NICs to get a higher bandwidth. Furthermore, you have latency sensitivity, which is unfortunately hard to measure, but also hard to optimize. So in some sense, latency sensitivity is really a matter of physics. So you cannot go faster than the speed of light. So it's also very hard to improve. So one of these axes, latency, is fundamental. The other one is a cost axis. This is going to play a role in arguing about data center deployments, of course. First of all, very bandwidth sensitive, but not so, but also latency sensitive computations are graph computations, as in the Graph 500. Then if you look at latency sensitive applications, but high bandwidth sensitivity, then we talk about scaling workloads and strong scaling HPC workloads. By the way, sorry, I made a mistake. It should be low bandwidth sensitivity and high latency sensitivity for the Graph 500. Also, weather and climate simulations, as you scale them up, become more bandwidth sensitive and more latency sensitive. These are actually quite hard workloads to scale in some extent. And LLM inference, going to very small messages sometimes, or relatively small messages. If you have low bandwidth sensitivity and high bandwidth sensitivity and low latency sensitivity, then you go much into weak scaling HPC workloads, very much like the traditional simulation, modeling and simulation workloads that many of us have, if they weak scale. And if they strong scale, they get more latency sensitive. If you have AI training as one of those workloads, that is basically the same thing. So AI training has very high bandwidth sensitivity, but relatively low latency sensitivity, nearly nothing actually. Then if you run low, you don't care about bandwidth and you don't care about latency, well, that's independent jobs. That's not really large-scale HPC because your CPU is mostly bored, but it may be a major business. Your network is mostly bored for those jobs, not the CPU, but it may be a major business, actually. Now the question is, how can we measure the latency sensitivity of real applications? It's a small detour, but an interesting one, I believe. Because first of all, if the application is sending very large messages, then it's less latency sensitive than sending small messages. But that doesn't mean much. It's less. It's on a general scale, but we don't know where the scale is. Furthermore, if we pipeline and overlap these small messages, we are also less latency sensitive than small messages on the critical path. That's also a very simple statement. But now, for a given application, how do we understand the latency sensitivity? Well, we need to look at the execution graph. And we look at the execution graph that is launched or created by essentially MPI or nickel-like applications, and we can look at a principle that's called message depth. So we have an MPI program, for example, which we trace, and we generate an MPI trace where we see all of these events, like when we call MPI init, com_size, and iReceive. And then we look at the execution DAG, or we generate from this trace an execution DAG where we can look at the critical path. Of course, the critical path varies with latency. As we change the latency sensitivity, some nodes or processors will get on the critical path, others will get off. This really depends on your parameters. But we find that you can express this as a linear program, and we can solve that linear program, and then we can do analysis. So this is actually quite an interesting, I would call it a breakthrough in this application analysis. If you can, the idea to express this as a linear program, because it makes it many orders of magnitude faster than if you run this in a simulation setting, which is another option. But again, many orders of magnitude faster. So now we can use this technique, and if you care about the details, I would recommend you look at this paper by one of my students, Xiran Chen, who's a brilliant student and came up with this idea together with Langwen Wang. And we look at various applications now, for example, the US QCD application, and we can now look at what network latency it needs in order to slow down the application by even 1%, 2%, or 5%. So here in this MILK application coming out of the US QCD program, 4.8 microseconds network latency will slow down, added network latency will slow down the application by 1%. And before it slows down by more than 5%, you can add 22 microseconds network latency. Now let's look at Lulesh, where it's interesting because a 1% slowdown is only reached with 17 microsecond added latency, and the 5% slowdown only with 65 microsecond latency. So that's a huge tolerance, actually. But there's even larger tolerance if you look at the icon code, which is a climate code which we run in a non-strong scaling configuration, obviously here. So we can add until 670 microseconds of latency before we get more than a 5% slowdown. So now we already see that various applications have various different characteristics in terms of their latency sensitivity, which is quite important to understand. Actually, the latency sensitivity can be measured by linear programs, but varies by 32 times between the most sensitive application that we measured and the least sensitive application that we measured, MILK and ICON respectively. So that's an interesting result, so you should try it for your application. You can download the toolchain and try the toolchain, or understand the method and build it into your own tools. So now the question is, how do these latency and bandwidth terms actually behave on real cloud and on-prem systems? Well, there's a study performed by Daniela Tesensi, a member of my group now, a professor in Rome, and many other people in SPCL that we had at Sigmetrics 2022. So note that it's already 2 years old in some sense, and these cloud systems may have changed. They get regular updates, but to most extent this is still true. So here we look at various cloud systems, and we look at half RTT, or you could call it the latency, in microseconds for various of these systems. You see, there are some standard networks that are relatively slow, so AWS, the front-end network, as well as GCP. They're just using the standard Ethernet network to transport high-performance traffic in some settings. AWS actually has a back-end network configuration as well. And then you see this band down here, which is generally less than 5 microseconds latency, which are optimized networks, on-prem or off-prem. So for example, in the cloud, so Oracle systems. So these are so-called specialized backend networks. If you look at the bandwidth here, it's a very similar picture. So we have a similar front-end networks are typically the standard old Ethernet networks, are typically slower in terms of bandwidth than the highly optimized backend networks. Okay, great. Well, there's another effect though that we need to pay attention to when we run systems in the cloud. And this is what we call network noise. Network noise is a very old principle. I wrote a paper about this on 15 years ago, but now it becomes relevant in the cloud. So what is network noise? So network noise is essentially where you have this execution DAG, where you have depending applications, your process 0, 1, 2, and 3, and 4, and somehow process 2 is delayed, and then delays the execution of process 4 because process 4 is waiting for a message from process 2. So you essentially propagate delays across node boundaries. So here in this case, process 2 is delayed. But what could happen, this is a delay on that process, but what could also happen is that two processes or two communicating processes share the same network resource. Here we have a fat tree network, this is a switch on the top, and here we have the red and the green conflicting on the same switch. They may be using the same output port, and they may congest each other. And what that means is not the node itself is delayed, but the communication to the node. And you can see here, communication between node 1 and 2 is delayed, which delays the reception of the message at node 2, which delays the message at node 4 as well. So we have now 2 nodes delayed, just with a single, through a chain of dependencies, just with a single network noise event, like we can see here. For example, this link runs at half the bandwidth because 2 output streams go on the same link. So now let's look at this in detail. How does this look like on the cloud? Because we can measure this. We can actually look at the expected latency. We can measure it every now and then, and we measured it over many, many minutes. So 1 hour total. We launched multiple probes. And then we look at the slowdown, going from 2 times slowdown, here this band down here is basically 1 time slowdown, no slowdown at all, up to 512x. So it's quite massive. We can have up to 500 times slowdown in terms of latency for single messages, for single packets in this particular case. This is the same rack configuration. If all of the nodes run in the same rack, if we run them on different racks, this is about the same. It's just the configuration changes, so the system names here change that have the bad configuration. So you can look at all this data yourself, but important to remember is that you can get a 500 times latency slowdown at, of course, a low probability event. So all systems see latency noise on-prem in this particular result, sometimes even more than cloud systems. But this really depends on the background workload. So you could now argue that these on-prem systems have higher production workloads and the cloud systems are always idle because you need conflicting flows to show this. We do not know any utilization data of these systems when we ran it, but you should pay attention to this. Very similarly, we could look at the bandwidth. So we could run the same experiment, and we could now go from full bandwidth, which is now the normal idea, again, 60-minute tracing, and then we measure the bandwidth, so normalized bandwidth, and we can go down to very, very, very small, close to 0 bandwidth configurations for some flows. This is not single packet flows like the latency. This is now multi-packet flows where we're actually transmitting significant data. And in different racks, we can go even to 1 gigabit per second. And remember, these systems run at 100 or 200 gigabit per second. So this is 1/100th of the bandwidth, a little bit more, maybe a 90th. And this is less than 1/100th of the bandwidth we are actually observing for some of those flows. And this is very apparent here for GCP, and then here in the, I believe this is the Oracle Cloud. Yeah, I had some of those hiccups as well. So cloud systems are much more affected by bandwidth noise. When sharing the front-end network, they're particularly affected. So this is another interesting insight that we gained. Now the question is, what is the impact of this noise? Well, we ran a dummy application, matrix multiplication, of course, this is what you do, together with an all-reduce. This is in fact very similar to any of these AI machine learning models. They run matrix multiplication and all-reduce. And then we simulate noise injection with our framework log-opsim. And then we see that we simulate operating system noise injection and network noise injection. So for essentially all of those systems, the network noise absolutely dominates the noise sources. So network noise is much more relevant than operating system noise, which is very different from 10 years ago where operating system noise was a big topic. But in many of these systems, it has been prevented over the last decade because we pointed it out as a big problem. Now network noise is back as the problem. Azure HPC, very similar. In fact, all of the cloud systems have very similar effects. So network noise is a huge effect, has a huge effect on the monetary cost to a percentage cost increase up to 20% higher costs just to run the same workload due to noise. So even low communication applications like this one can increase the cost significantly up to 20%. So this should also make us worry about the future of cloud. At least we should understand how to run these applications. I mean, at the end they just run 20% slower. So now the question is, Well, this has been run on all these existing interconnects that I talked about before. Like every cloud has a different interconnect, every on-prem system has a different interconnect. Which is the right interconnect? What's the best one? Well, if you study the data before, it's pretty inconclusive. But one thing is pretty obvious, because Ethernet is the elephant in the room. Ethernet ships 600 million ports annually. That's more than 1,000 ports per minute, actually. So while I'm talking here, thousands of ports are deployed worldwide of Ethernet. So this is a market we cannot ignore. And this is a market that is going to grow even bigger. But however, Ethernet is not the same as Ethernet, because you could be running TCP/IP over Ethernet, or you could run RDMA over converged Ethernet over this Ethernet. By the way, RDMA over converged Ethernet, short RoCE, should really be called InfiniBand over Ethernet, because it's just an InfiniBand packet strapped on top of an Ethernet header. But now, how do we go about this? How do we converge this HPC network mess into a unified Ethernet-based standard for high performance in AI? Well, you could argue that there's RDMA over converged Ethernet. This already exists. We could run this today. But unfortunately, it does not fulfill the needs of all mega data center providers. So there are many issues at hyperscale. We wrote a paper on this in 2023, which I recommend you look at in detail to understand why these issues are there. I will explain some of those in the next couple of minutes. Based on these observations, we founded the Ultra Ethernet Consortium, and I was involved as Microsoft representative, as one of the founding members, and came up with a new idea to design a specification, Ethernet-based specification for high-performance computing and AI. And you can read the white paper to understand what really the idea is, but you can also listen to me for the next couple of minutes and I will give you some more insights. So the ecosystem of Ultra Ethernet is quickly growing. Today we actually have 10 steering companies, 18 general members, and 25 contributing members. That was actually at the time of Salishan when I recorded this talk. I believe today we have more than 83 companies total in Ultra Ethernet, represented in Ultra Ethernet, so it's quickly growing. It's extremely quickly growing. In March 24, at the Transport Working Group meeting, we had a whole lot of people, more than 60 people in the room. So this is my empty computer here because I was chairing the meeting at the time together with my wonderful co-chair Karen Schramm, who's doing a wonderful job of herding the cats and keeping the forum together, actually. So she's great. But now let me go a little bit more into details of what makes RoCE a tough sell. So first of all, RoCE bases on PFC, priority flow control, which is really a lossless interconnect. So Ultra Ethernet wants to run lossy as well. RoCE does not run lossy. So it runs, but really, really slowly because the protocol is not optimized for it. We define a new transport protocol for Ultra Ethernet that can deal with lossy networks. So now the problem with lossless, with PFC, priority flow control, is that you require switch buffers that are proportional to the bandwidth in the switch. And switch bandwidth doubles every 2 years. So now that is a problem. It also requires, the switch buffer is also proportional to the length of the cable. So now if you look at the wire delay here, which is essentially 5 nanoseconds per meter, so it's the length of the cable, going from the cluster length, 150 meters, to 1,000 meters for a data center site for a 400 kilometer region, up to 6,000 kilometer global. And this is a log scale here. So we may need a gigabyte of buffering per port if we go to the whole region at 800G, and that is a huge problem. So it's only megabytes in the cluster, but if you scale this to a global scale, like many data center providers envision, then you will have a huge problem. So lossless is an issue. PFC is an issue just due to the buffering. Furthermore, there is a phenomenon called victim flows where congestion trees build. So for example, if you have a source communicating with a target here through 2 intermediate switches or repeaters, source 1, this is the switch, is another switch, and this is the destination. And the destination has another 4 streams coming in, which means it receives from S1 at 1/4 of the bandwidth. Now it back pressures through PFC all of these links to run at 1/4 of the bandwidth if they share the same traffic class. Now if you have another source sending to another destination, actually this destination is uncontended, this T2, and this could be sending at full bandwidth, actually at least at 3/4 of the bandwidth, because this link is still shared. What will happen is that due to PFC, this link will also only send at 1/4 of the bandwidth. So now we are wasting half of the bandwidth of this intermediate link between these two S2 and T2. So this is pretty sad. This is called head-of-line blocking, and sometimes congestion trees form to make the overall performance much slower than it should be. If you have an unlucky configuration where these dependencies are cyclic, you could create deadlocks in your network. Furthermore, go back and retransmission in Rocky is quite inefficient. I don't want to go into too much detail, but it's really the idea that you resend the whole stream of packets that are on the wire could be quite inefficient. Congestion control of collocated traffic is another issue where you have to deal with in this context of mega data centers, because you may have different traffic like video streaming on the same traffic class, which may be very problematic if you want to co-locate Rocky traffic with it. So you must have address many of these issues. And again, I just showed you 4 examples very quickly. There's a list of, I believe, 10 or 12 of these issues in the full paper that you can download from the IEEE or also from arXiv, and you see the link down here if you care about all the details. But now, going forward, this was the complaint about the past. How do we deal with this in Ultra Ethernet? Well, I can't talk about too much because it's still confidential, but there are multiple blogs now that are published on the Ultra Ethernet webpage, which you could go through. But let me summarize what these blogs say. Well, first of all, Ultra Ethernet bases on the Ethernet physical layer in a close collaboration with the IEEE 802.3 standards body. So that's quite nice. And then it slightly extends the Ethernet link layer. So there are some extensions that benefit AI and HPC workloads. For example, there's an introduction of a lossless credit-based traffic class or credit-based traffic transport or point-to-point link that we could be talking about, but I don't want to talk about at this point because there will be other people talking about this. And then we have the IP layer, which remains untouched, also in Ultra Ethernet. And then we have the transport layer, which is essentially completely redesigned for Ultra Ethernet. All the green things are the same or very similar to Ethernet, definitely Ethernet compatible, which means you can run Ultra Ethernet over your old existing network infrastructure without any problem. But now the blue thing is completely redesigned. The transport layer, semantics layer, packet delivery, congestion management, and reliability, as well as security. So this is the real big news. This is discussed in the transport working group, the blue layer, which is the most massive working group. And as I mentioned, I'm one of the co-chairs of this working group together with Karen Schramm, and we have the honor of driving this this innovation through Ultra Ethernet. This has painful, but also lots of rewarding moments. And at the end, we run libfabrics and Ultra Ethernet with some Ultra Ethernet extensions on top of this, and then hopefully run unchanged libfabric applications on top of the whole stack. So really the idea is to just exchange the transport mode. So at the end, we are enabling cheap high-performance hardware implementations with an optimized transport port over legacy Ethernet networks. Well, this all enables vendor innovation. Like, vendors can differentiate, they can add features to these old Ethernet networks to make it even faster. So this is the ecosystem idea. For this transport, we have a little bit of a refinement, but I already talked about this. So we have the semantics layer, packet delivery layer, congestion management, reliability, as well as the security sublayers. So these are sublayers in the transport spec. Each of those is about 40 to 80 pages, depending on which one you look at. So it's quite a massive definition, and I can't go into too much detail at this point because it's still confidential for a couple of weeks. But what I can tell you about is the key features, what we are planning to work on, compared to Rocky and others. So first of all, we want to enable lossy, which we call best effort, and also lossless operation, which solves all the blocking operations if you go lossy, of course, if you go best effort. We want to support flexible ordering, reliable ordered delivery, unordered delivery, and unreliable unordered delivery. So we have various ordering modes in the spec itself. We want to supply a state-of-the-art, easily configured congestion control mechanism that is compatible. In the next version, we are talking about other mechanisms that could even be extensible, and we want to support packet trimming as an extension. Furthermore, multipath packet spraying is one of the key fundamental ideas in Ultra Ethernet, but using existing technology, something like as it's called ECMP, equal cost multipathing, where you basically source route not really source route, but you select an unspecified route through the network, providing an entropy vector, an entropy value to each packet. Furthermore, we support switch offload and network collectives in the future as cheap and effective as possible. And we design the whole network as with security in mind as a first-class citizen, which addresses all these issues that my research group raised in terms of red mark, bypassing RDMA security mechanisms, mostly in Rocky systems, pretty scary. So you should read those if you're operating a Rocky system in a shared environment. And then sRDMA inspires many of the mechanisms that are employed in Ultra Ethernet now, which is our idea to make it secure in some sense. And then we have these Ethernet link and physical layer enhancements that are all optional. So this could all run on top of existing Ethernet. Now, let me dive a little bit deeper in the congestion control mechanism. We published a paper which is serving as a basis of that congestion control mechanism together with multiple people. You can see all these companies here involved, like Microsoft, AMD, Broadcom, and also my university, ETH Zurich. So I don't want to go too much into the data in this paper, but really the proposed algorithm outperforms pretty much all algorithms that there exist today. It's called the SMART algorithm. It stands for Sender-Based Marked Rapidly Adapting Trimmed and Timed Transport Protocol. It's a little bit of a mouthful, but it sounds cool if you pronounce it as a single go. And it's very simple. So it's essentially only 37 lines of simple pseudocode. In fact, with the help of the Ultra Ethernet consortium, this was refined and improved for the final version even. So this is an even slimmer implementation now, and while not losing many of the benefits. You can see lots of results. I don't want to go into too much detail, as I mentioned, but you could look at this paper to get a little bit of a preview. It is not exactly the algorithm that is in Ultra Ethernet, that will be in Ultra Ethernet, because many more companies have contributed to this, many additional discussions have led to it, but it heavily inspired the Ultra Ethernet final. Well, we're still debating the final version, but it heavily inspired the version that is most likely going to show up in the specification. So now, as a summary, I mentioned that everything is, or much is moving into the cloud or in cloud-like environments. So even on-prem data centers, on-prem computing will look like cloud-like environments. I strongly believe we need to understand the software stack for this, especially for accelerated systems, where the idea comes in of XaaS, acceleration as a service. I went into much detail. Then I talked about network performance metrics. So how do we actually compare on-prem and cloud network systems? These were all quite interesting data points, which all served as a motivation and as a basis for creating the Ultra Ethernet Consortium, really understanding how we can serve HPC and AI in the future as a large industry body, where basically all the networking companies that exist today are members of, and hopefully provide products in the relatively near future. And then I also talked a little bit about the congestion control algorithm, which was one of the contributions that many companies and universities made to that Ultra Ethernet specification. So really, this talk was all about acceleration as a service in Ultra Ethernet. And if you're interested in any of these topics, we're always looking for good PhD students, postdocs, and academic visitors. Thank you very much.